This is going to be homework 3. This is going to be homework 3, part 1A1. Some would say that I procrastinated. I would say I waited until I was home for spring break to use the big whiteboard in my basement. But anyways, we're going to be finding how much heat is needed to do an expansion or a compression of an ideal gas. And we're going to be deriving this from the first law of thermodynamics. So we'll start with du is equal to dq plus dw. And because it is isothermal, reversible, we'll change it to Cv dt is equal to dq rev for reversible. And because it's reversible, we'll end up with our differential amount of work being equal to P dV. And because it's isothermal, our dt is equal to 0 in this case. So we get dq rev is equal to P dV. And from this, we know, since it's an ideal gas, we know that PV equals nRT, but in this case, this is for 1 mole of gas, so we just have n equal 1 for now. So P is equal to RT over V, so we'll substitute that in. RT over V. And now we'll take the integrals to get rid of the differential amounts. And this V will be on the inside. And this RT, for now, is just going to be a constant. And the limits of our integration will be from 0 to Q. And then we'll have T1 to T2. From this, we get our Q reversible is equal to RT times ln of T2 minus ln T1, or just Q rev equals RT times ln of T2 over T1. And that is how you find the amount of heat needed to compress or expand for an isothermal reversible change. For part A2, we'll have a very similar situation. However, this time there's an adiabatic change, meaning our dq will be 0. However, this also means that our temperature may be changing. So it'll start very similarly. So U equals dq plus dw, and this is also an ideal gas. So our Cv dt 0 plus, well, not plus, minus, since it's reversible still, even though this is 0, it's reversible. However, that still means that this will be our P external will be equivalent to our P internal, so it'll just be P dV. And again, we'll substitute this P, PV equals RT, so P equals RT over V, and that will give us Cv dt equals negative P, or not P, negative RT over V times dV. So our V can just be moved over here. However, our t is no longer constant, which means we'll have to move on to the other side. So that will give us CV dt over t is equal to minus r times dv over v. And now we can take the integrals and our limits. We'll have t1 and v1 initials, and then v2 and t2, or the finals. And that will end up giving us CV ln of t2 over t1. That will be equal to r times the ln of v1 over v2. And we just got rid of the negative by having the reciprocal inside the natural log. And now we'll take this r over here, meaning we can put this up to be to the power of, meaning we can get rid of our natural logs. So that'll give us t2 over t1 to the CV over r is equal to v1 over v2. And now that we have this, we know that p1 v1 is equal to r times t1. We also know p2 times v2 equals r times t2. So using this, we can solve for t over r. Doesn't matter because it'll just cancel out. So we'll get p2 v2 over p1 v1 to the cv over r equals v1 over v2. And using a little bit of algebra, that can be simplified more so into p2 v2 to the cv plus r over r. Sorry, this is p2 to the cv over r. That will equal p1 to the cv over r times v1 to the cv plus r over r. And this is an important time to note another equation, or h equals q plus rt. And this has been given us for enthalpy. And if we were to take this with the derivative with respect to time, we'd get dh over dt, dq over dt, and r, which simplified is cp equals cv plus r. And as you notice, we have our cv plus r here, and that also shows up down here. So we're going to do two steps in one. Is we're going to replace our cp for cv plus r, and we're going to raise this entire equation to the r to get rid of the r in the denominator down here. So I'll probably move up here now. So we get p2 cv times v2 cp, and then we get it equals p1 cv v1 cp, and then we'll raise both sides to the 1 over cv, which will end up with p2 times v2 to the cp over cv, which will be equal to p1 to the times v1 to the cp over cv. And it should be noted that cp over cv is equal to the specific heat ratio, which can be denoted by K. should also be noted that P1 or P2 times V2 to the Cp over Cv, which is a constant, will be equal to P1 times V1 to that same constant. And this would be true for any combination of P's and V's, meaning we can essentially make this equivalent to the constant itself. So we'll end up with PV to the Cp over Cv is equal to a constant. And again, earlier, we have our PV equals RT. We'll replace RV with RT over P. So P RT over P. And that's to the K equals C. So we now get, this would be P to the minus 1, and then this R to the K will just be essentially another constant, meaning we'll just be able to move it over. So what we end up with is P to the 1 minus K, because of this P to the negative K down here, times T to the K is equal to C. And if we were to divide by P, that would be the negative of what's up here. So we end up with TK is equal to C times P 1 minus, K minus 1. And this would be the relationship between pressure and temperature and volume for an adiabatic reversible compression or expansion.